Sorry, the same problem like from in the morning, there was some network issues. I was not able to log in. So let me share my screen. Okay, you are able to see my screen, right? Hello?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So in continuation with our earlier discussion, so I'm going to discuss about lasing action and characteristics of laser. So we have seen what are the conditions that requires for light amplification, right? So how do we put that? So till now what we have seen is completely in a theoretical way. So what are the conditions that require and how can we achieve those conditions? So how do we put these conditions into practicality? Okay. So for that purpose, we need to see what are the components of a laser. Okay. So in laser, we have three main parts. That is, first one is active medium. So where actually this laser action takes place is called an active medium. Okay, where which the material, the crystal where we actually produce the wave, produce the laser is called an active medium. So in this active medium, there will be different types of atoms. Okay, so suppose as I said, to achieve the metastable states, we need to dope the particular material. Okay, so there will be different kinds of atoms will be there in the active medium, but not all the atoms are eligible to participate in the lasing action. Okay, there are only few atoms, that is a small fraction of atoms will be able to participate in this lasing action, and these atoms are called active centers. Okay, these atoms are called active centers. Only these particular atoms are able to achieve the population inversion. Okay, these are called active centers. But what about the other atoms? Other atoms are will be like a host. Okay, the other atoms which are in the other atoms are called host. Okay, and they support the active medium. Okay, they support the active centers. Okay, so this is the typical schematic diagram we can say of a laser, where this is the active medium will be there, and which will be pumping this active medium so that the atoms will atoms can be raised to the higher energy level. Okay, and this once we have done, then the photons will be developed, photons will be produced or emitted, and these emitted photons will move back and forth in between these mirrors. This is 100% reflecting mirror, whereas this is partially reflecting mirror, and from this partially reflecting mirror we'll get a laser beam. Okay, this whole thing is called optical cavity. We have seen in the morning, right? Optical resonating cavity or optical resonator. So this particular one is called optical resonator. Okay, pump will be outside the optical resonator. The active medium, which is placed in between the two parallel plane mirrors, is called optical resonator. So from this from the partially reflecting mirror, end of the partial reflecting mirror, will get a laser beam. Okay, so this is how it will be. This is a schematic diagram. So the first component is active medium. Now the second component, that important component, is the pump. So the pump is an external source that supplies energy needed to transfer the laser medium into the state of population inversion. So we know that we know that always the N1 is greater than N2 in the normal conditions. But what we require is N2 much greater than N1. So to achieve this population inversion, we need to supply energy continuously to the laser medium. Okay, this particular medium is called, this particular thing can be done by pumping. So as I said in the morning, there are different pumping techniques. One is optical pumping. In optical pumping, this is used basically in solid state lasers. One, what is optical pumping is we shine the material with the light. Shine the material with light. Okay, we shine the material with light so that the energies. So that is what actually basically we have been discussing. No, the photons can be photons can be shown on the atoms, and the atoms absorbs the photon and leaves the lower energy state to reach the higher energy state. So this is what actually that is what we call optical pumping. Shine the material with the light, and this can be done. This pumping technique used in solid state lasers. Okay, the second one method is electrical discharge. Electrical discharge is sending electricity into the active medium, but we have to make sure that this electricity should not destroy the lasing medium itself. Okay, so that's why usually this electric discharge method is used in gas lasers. So these electric discharge tubes, or there will be something like electric fast charging tubes. Okay, so these from these kind of techniques, so they send the electricity into the gas medium. Then these because of this electricity, the atoms get ionized and raises to the higher energy levels. Okay, and then the stimulated emission happens bigger, and this will be continuously done using this electrical discharge will be continuously done, so that we'll be able to get the laser beam. Okay, there is another method which is called direct conversion. In direct conversion method, the electrical energy is converted in, the electrical energy is converted into optical energy. So this electrical energy will be directly converted to the optical energy, and then that will be used to change the that will be used to get the atoms to higher energy level. Okay, this direct conversion method is used in semiconductor diode lasers. Okay, so this is the pumping. These are the different types of pumping techniques. Of course, there are other methods also, but these three are main important or well known for the lasers. Okay, so the second component is the pump. Now the third component, third one is another. So as you can see, these three conditions, these three out of these three important things, these two are very important: optical resonator and the pump, because we need to achieve the three conditions that need to be satisfied to get the lasing action. So this is the third one is optical resonator. So optical resonator is simply like this active medium placed in between these two. Okay, so as you can see that this is now like analogous to an electronic oscillator. Okay, or in electronic oscillator, what happens is it is like simply like an amplifier which has an input. Okay, and then we get an output. Again, this is feed into the this is fed back to the input. Okay, so this is how it works. So this will be your V naught and this will be your V in. Okay, so we'll be sending an signal, and the output again is fed to the input. Okay, so this is what we call an electronic oscillator. This is what will be done in electronic oscillator. So in laser also, this is what we do. So a pair of optically plane parallel mirrors or so mirrors and enclosure laser medium in between them is known as, this is what we sorry so we keep an active medium in between two optically plane parallel mirrors. Okay, in which one of them is 100% reflecting mirror and the other one is semi transparent mirror. Okay, so here in between what happens is whatever the first what happens is spontaneous emission will take place. Okay, first spontaneous emission will be takes place. So what happens in spontaneous emission? in spontaneous emission, the atoms themselves lose the energy, and so the atoms in the higher energy loses energy on its own and reaches to the lower energy level. Okay, how do they lose the energy? In form of photons. Now these photons, what happens is these photons will be in different directions. Okay, they'll have different phase, they'll be different direction, they'll have different frequencies. Okay, but whatever the photons whatever the photons which are parallel to the optical axis of this plane, optical axis of the optical axis between these two mirrors will be reflected back and forth. Okay, so the optical coherence, so this is what happens. So optical cavity selects and amplifies only certain frequencies, causing the laser output to be highly monochromatic. So whatever the photons whichever are parallel to the optical axis of the transparent mirrors, they only get selected, and they will be reflected forth and back. Okay, so what happens is here, so we have discussed in the morning. So once when these photons are emitted, on their way they again stimulate the atoms in the higher energy level and gives rise to an extra photon, right? So this is spontaneous emission. So it stimulates this photon and emits two other photons. Okay, so there will be many number of photons which will be going in this direction, which will be participating in this, which will be in this what is this called, optical axis. Okay, so all these photons which are in this direction they will be automatic, they will be reflected back, and from here again they will be reflected back, so that on their way again they will stimulate the other atoms in the energy, other atoms in which are in the higher energy state. Okay, so what happens is lazing action. So as I said just now, we have seen there will be three particular components are there. So how does this lazing action takes place? It's just now actually I have almost explained everything. So in step one there will be pumping. Okay, so the atoms, so here you can see this one. So in the first figure A, these whatever the black dots are called active centers. Okay, these are active centers, and others are host materials. Okay, there are, this is active center. The black spots are active centers, and the white, the whole white area, what we call as host material. So this is the black one is completely reflecting mirror, and this partial semi-transparent mirror on the right side we have it is with dashed lines. Okay, it is filled with dashed lines. So what happens here is first we'll be doing the pumping. That is, we first send the energy. We will first send the let's say optical pumping. So first when we use the optical pumping, then all the atoms will be, most of the atoms which are in the ground state, they will absorb the photons and move to the higher state. Okay, then because of the metastable states, the population inversion will be happening. Okay, because of the pumping, all the atoms which are in the lower energy state, first there will be very few atoms in the higher energy state. After pumping, then there will be more number of atoms in the higher energy state, and less number of atoms in the lower energy state. Okay, this is what we call population inversion. Okay, this is what we call population inversion. So here N2 is greater than N1. So this can be achieved by using the pumping techniques, and we make sure that the higher energy level has a larger lifetimes. larger lifetimes. Okay, once this is done, once optical pumping is done and the population inversion is achieved, then the spontaneous emission happens. So once even though it is larger, but there can be the atoms cannot stay more than 10 power minus 3 seconds. They cannot stay more than 10 power minus 3 seconds in the metastable state. Okay, this is the maximum, and the minimum is 10 power minus 6 seconds, that is microseconds. So time scales, in between these two time scales, the atoms will emit photons. They will be emit photons and move back to the lower energy state because of the spontaneous emission. Okay, this is the third step. So this is the optical pumping. The atoms, so we are sending, so you can see it graphically. So we are sending the photon inside the material. Okay, now what happens is because of the spontaneous emission, so here the black, as you can see that this black is turned into white. That means the atoms have left their places. Okay, and in this direction, and when they are emitting the photons, as you can see, there will be different direction. The photons will be emitted in the different direction, but there are particular photons which are parallel to the optical axis of this cavity. Okay, let's say this is the optical cavity will be like parallel to this, just like in whatever we take at an x-axis. Okay, so there will be some photons, as you can see, this particular one, this one, this one, and this one, this one, and this one. So these photons are traveling parallel to the optical axis. Okay, once they reach this semi-transparent mirror, again they will reflect back from this portion. Okay, then they will again go back. When they are traveling back to the reflecting mirror, completely reflect 100% reflecting mirror, again they stimulate the atoms. Okay, they stimulate the atoms which are in the higher energy states, and then again they will reflect back. Okay, so because of the stimulate, they stimulate the higher energy atoms, there will be more photons will be generated here, and when they come back, so as you can see here, this is stimulated emission will be happening here. So there will be photons, these photons will be coming here, and again these photons will be reflecting back here up to here, and from there again there will be photons will be traveling in this direction. So as you can see, these are the photons which are parallel to the optical axis, these photons. And now after from here, they are reflecting back. They are reflecting back. And on their way, they will be stimulating other atoms. And once they reach here, and again from here, there are more number of photons are generated. Now this again, they will be going back to here. Okay. Now, what happens? See, do all the photons from here will be reflected? Do all photons reflected? No. From here, from this space. Because this is not 100% reflecting mirror, because this is a semi-transparent mirror. Because of the semi-transparency, what happens is there will be some loss of the light. Okay, there will be some loss of the light in at this point, or loss of photons. Okay, there will be loss of photons in this, but in this at this mirror. Okay, but there won't be any loss at this mirror because this is 100% reflecting mirror. Okay, so what happens is there will be, because of course there is a loss of photons, but there will be a gain at this point. Okay, there will be a gain at this end. So when this loss and the gain, there will be loss here, there will be loss of photons, and here there will be gain because of the reflection, because there will be completely reflection of photons will be stimulating the other atoms. So when these things happens, there will be gain. Okay, when these atoms are coming back from this mirror, there will be gain. That is, number of photons will be increased because they will be stimulating the atoms in the higher energy state. So when this gain equals to loss, when gain equals to loss, then we say that there will be a steady state will be achieved. Okay, but the loss will be partial. Okay, so here not all the photons are not all the photons are not losing. Okay, we are not losing all the photons, but there are a fraction of photons we are getting it back. But here we will be getting 100%. So that sometime at first some point the gain will be equals to loss, and after some time this gain will be more than loss. That is, the number of photons generated will be more than the number of photons that are leaving from this place. Okay, at that point, as you can see that the density of the photon density is increasing from one step to other. When there is a particular index, when there is more gain than the loss, then we can see that the laser beam is coming out of this particular phase. Okay, this one, this is after the loss. So okay, we have lost the amount which we cannot be controlled. Okay, at the end, when we get gain more than loss, we'll be having a laser beam. Okay, we'll get a laser beam in this direction. Okay, so this emitted laser beam will be very high intense and will have very high intense and monochromatic. Sorry. Monochromatic, because only particular frequency of the, see, as you can see here in this step, there will be only particular frequency of the energy, or the particular energy of to axis of this cavity. Okay, that's why they will be monochromatic, and because of this, so many number of photons will be coming out of this particular phase of, or this particular mirror. Because of that, they will be high intense. Okay, so this is how what a lasing action. This is how the laser is produced. So, are there any doubts at this point?
Stimulated emission, sir. Once again, let's say about stimulated emission.
Stimulated emission. This one.
Upper, so C.
See, yeah. See, what happens here is, see at this point, see here this optical pumping, we have given the photons. Okay, as you can see that we are giving the photons here. Okay, I think they have mismatched it. Actually, this is spontaneous emission. This particular one is, this is actually spontaneous emission. This is stimulated emission from this. Actually, in the textbook, I think they have given it wrong, because as you can see from the spontaneous emission, the photons will be moving in different directions. Okay, this is going in this direction, this is moving in this direction, this is in this direction. Okay, so this is actually spontaneous emission. The photons are moving on their own. The photons are emitted because the atoms, atoms move to the lower energy level on their own. Okay, so that's why they are in the different directions. But of course there are in the different direction, but there are some photons, this is also randomly they happened, but they are parallel to the optical axis of this cavity. Okay, they are parallel to the parallel to the axis of, sorry, they are parallel to the optical axis of the optical cavity. Okay, so these photons will be selected, and these photons, out of these photons, they will be reflected, partially reflected. Some photons will be reflected from this particular mirror, and of course there will be some loss in this direction. Okay, so in this, from here, these photons which are coming in the parallel to the optical axis are reflected back. So this is what we call optical feedback. Okay, as you can, if you can now note, see this. So this is what we call optical feedback. So the amount, whatever the output we are getting, so this is an electronic circuit, as I said. Let's say this is connected to a battery. Now this, again we are giving this output to this one. Okay, so this is something looks like an electronic oscillator. So here what we are doing, this is what we call a feedback. Okay, so whatever the output we are getting, we are giving it back to the input. So here also we are getting whatever the output we are getting from the spontaneous emissions, we are sending it back. So this will be continuous process. Okay.
Okay, sir.
So are there any others? Any others have any doubts? I'm sorry, why this is not coming? No doubts? Okay, so I'll move on to the next topic. So this is how the laser action is lasing. So this is how the lasing action takes place. Okay, now what are the characteristics of this laser beam? Whatever the laser beam that we have got, what are the characteristics of that? So why so much fuss about this laser? Is because of these characteristics. So the important characteristics are directionality, negligible divergence, high intensity, high degree of coherence, and high monochromaticity. Okay, so we'll see particular what are these characters. How do we get this?
So once backslide.
Is there anybody writing down the notes? Do you want me to give some time to write down?
Yes, sir. Yes, sir.
Okay, so write down these characteristics. The first one is directionality, negligible divergence, high intensity, high degree of coherence, and high monochromaticity. So you can write down later also, because we will be dealing the same properties here. So the first one is directionality. So the conventional light source emit light uniformly in all directions. Okay, but light travels in a specific direction when a slit is placed in front of. So all of you have done diffraction experiments, right? So some few of you have done diffraction grating, and some of you have done this single slit experiment, right?
Sir.
So what happens there is, so when there is a light is, so what happens there is light travels in a specific direction when a slit is placed in front of the light source. So what does that mean? So when we put the slit or the diffraction gratings, we have seen the fringes, right? So there will be a dark spot in between. So of course we have used instead of a monochromatic light, I mean instead of a normal light, we have used laser light. Okay, so that's why you might have seen spots like this, a bigger spot like this, and then here, and then go something like this, right? So this is how it actually occurs. So otherwise, if we are using a conventional light source, then we'll have a fringes which looks something like this. Okay, so this is the interference pattern or the diffraction pattern that we see. Okay, so in case of laser, the active material is in a cylindrical resonant cavity. Only the light that is traveling parallel to the axis is selected and reinforced. So that means reinforced means again we are giving the back strength. Okay, so just okay. Okay, so only the which are so just now we have seen that in lasing action. So we have seen the photons which are parallel to the optical axis are only selected and reinforced. That means we are getting it giving the optical feedback type of thing. So only those photons are reflected back. Okay. So what happens to the other? So we have seen here. So what happens to these photons? These photons which are moving from here, which are going in this direction. So these photons will be moved out, and they lost. We lost for them for like we lost forever. Okay, we lost them forever. But how? Where they will go inside the medium? So these are the photons. Actually, they dissipate in the form of heat. Okay, they convert into heat, and the active medium will be little bit a little bit at a higher temperature. Okay, so that is why usually we'll keep the lasing system inside a cold room. Okay, so because the light that is traveling parallel to the axis is selected and reinforced, that means light only will get a particular direction of that. Okay, so that's why the light propagating along the axial direction emerges from the cavity and becomes the laser beam. Thus, a laser emit lights only in one direction. Okay, only in one direction. As you can see that at the output, the direction of the all the photons are in the same direction. Okay, that's why it is a highly directional. Okay, the second important thing, important property of the laser is the divergence. So light from conventional source spreads out in the form of a spherical wavefront, and hence it is highly divergent. So this is how actually this ordinary light source travels. Okay, they travel in this like this. Okay, they travel in the circular wavefronts. Okay, that's why, as you can see, if you're in a dark room, if you switch on a torch light, you can see directly, you can see it will something, the light focus will be something like this. Okay, so the divergence from the source is very high. Okay, whereas on the other hand, whereas from light from a laser propagates in the form of a plane waves, that is the what is a plane wave? So wherever you see the value of if you cut a plane wave, so if you look at through the value of a plane, then it will have the same value at all the planes. Okay, suppose you have a wave traveling like this. So if you look at different waves, so if you look at through a particular plane, if you look at a particular plane, all the waves will have a same value. That's what we call as plane waves. Okay, so the light beam remains essentially as a bundle of parallel rays. So whatever the value, so there will be different lines here. So at any plane, if you take any plane, a particular plane, then all the rays will have a same value. Okay, so that is what plane waves are. So the light beams which are in the light which comes out of the laser or plane waves. That's why there will be a small divergence that exists due to the diffraction beam at the exit mirror. Okay, so a typical value of divergence of helium neon laser is 10 power minus 3 radians. That is, you can imagine how small this angle is. Okay, that is 0.001 radians. Okay, if you can imagine 1 degree, that is pi by 180 radians. If you convert 0.01 to this one, you can imagine how 1 radian, 1 degree is. It will not be even this much distance. Even I cannot draw this. So, but the divergence value of this helium neon laser is 10 power minus 3. Okay. So if the diameter of so yeah, have you, you all have done this experiments, right? So on the screen, when there is no slit or the diffraction grating, you have seen a particular spot, right? The red spot. We have used helium neon laser only. You have seen the light, right? A spot, right? Yes or no?
Yes, sir.
So this spot, the diameter of this spot, if you increase or decrease the distance from the screen without split, without any grating or the slit, what happens is this increases or decreases, right?
Yes, sir.
Yes. So suppose if I have a laser source here, if the distance, this is the screen, then the distance from here to here, if I increase the spot, if I increase the distance from here to here, then the spot increases, right? The radius of the spot is increases. You have observed it, I guess, right? Yes or no?
Yes, sir.
So if you take the different lengths, and if you can calculate the diameter of the spot, then the divergence is given by this value. Phi is equals to d2 minus d1 by L2 minus L1, whereas the d1 is the spot diameter, and d1 and the d2 are the spot diameters at L1 and L2. So this value will be equals to 10 power minus 3 radians in case of helium neon laser. Okay. So the intensity. So as I said, this will be very highly intensive because of the because of the optical cavity. Okay. So the light intensity will be given by I is equals to 10 square by 10 by lambda whole square times P, where P is the power radiated by the laser. So that is that we can calculate. This is the power of the laser. So the intensity is given by this much. Okay. So because it see what, how do we measure the power? So it is the force experienced. So as you can see that here. So what is the force that is actually applying on a particular area? Okay, from the figure. Or if you can calculate, or you can calculate what do we call, using an electrogalvanometer, we can convert that into optical energy into electrical energy, and then we can calculate the intensity there. Okay, so we can calculate the intensity of the laser beam from this condition. Okay, so and of course it depends upon the distance also. Okay. And coherence. Coherence is, as we have discussed already, we have discussed so many times that all the photons which are emitted from the stimulated emitted radiation, they will have same phase and same frequency, almost same frequency. The difference between the frequencies are very small. Okay, so how much distance? So how do we calculate this coherence? Okay, how do we measure the quality of the coherence is based on coherence length. Okay, so that is coherence length. How do you define coherence length is how much distance they will be in the same phase, how much the travel let's say the laser is coming out from this mirror. So if we can calculate the distance from this point to where actually they start diverging in the phase, in their phase is of 100 meters. Okay, A laser has a coherence length of light 100 meters, whereas in an ordinary source, at a monochromatic source, it has a source order of 0.3 millimeters. Okay, so that is the coherence length. That is the coherence length. That's why we say that the laser light has so much coherent. Okay, and the last characteristic, important characteristic of that laser is monochromaticity. So, like as we seen, if light coming from a source has only one frequency of oscillation, then the light is said to be monochromatic, and the source a monochromatic source. Okay, that means if not only laser source, any particular source is emitting a monochromatic frequency, that is a particular color. So any color, that means it will have only one frequency. But however, there is a light traditional from monochromatic spreads over a wavelength of 100 angstroms to 1000 angstroms. Okay. On the other hand, the light from lasers is highly monochromatic and contains a very narrow range of 10 less than 10 angstroms. Okay, so that means the spread of the frequencies. So even if you say that it's a light is of a particular color, there is a mixture of other frequencies, other colors also. So that frequency range or the wavelength range is from 100 angstroms to 1000 angstroms. Whereas in the laser light, that mixture will be less than the 10 angstroms. That is the spread of the frequencies or delta nu is, or here you can say delta lambda will be very much less than 10 angstroms. Okay, so that's why we can say that the laser is a monochromatic light. Okay, I mean the laser beam produced is monochromatic light, not the laser itself, because laser is a source of generate light, not the light itself. Okay, so these are the characteristics of the laser. So are there any doubts as